Good morning, everyone. I'm Sue Lessica. I'll be presenting this topic today on behalf of Bill Corwin. He had a previous engagement, wasn't able to join us, so he asked me to fill in, so I'll endeavor to do his presentation justice. So the grand challenge in this area is developing structural materials that support our advanced fission reactor designs. And as these designs come together under different operating conditions, new, more advanced materials are needed in order to survive and thrive in these very challenging environments. Three different types of reactors that are of interest currently are gas-cooled reactors, the sodium fast reactors, and the fluoride salt-cooled high-temperature reactors. These are of interest both in the large-scale reactor designs and also in the small modular reactor designs. So with these different coolants and these different operating conditions, different structural materials are needed and to be designed, to be codified, and to be well understood in order to be used in these designs. They also, in order to be used in these designs, manufacturability is also an important part, and jointability and being able to understand what is going on at these joints as well. To give you a little context on what the programs are focusing on, to give you some context on for the materials work, there's two programs that are supported by this work, the Advanced Reactor Concepts and the Advanced Small Modular Reactor program. The ARC, which is the Advanced Reactor Concepts, looks at R&D for fundamental nuclear technologies. These are mainly large-scale reactors. Currently, the focus for materials research in this program are developing alloys for the sodium fast reactor, both ferritic and austenitic steels. And for the next generation nuclear plant, the interest there is in graphite and alloy 617. Both of those are of interest due to their very high temperature, their ability to work in very high temperatures. The other program, the Advanced SMR program, supports looking at smaller designs and with longer licensing horizons. And the materials of interest in that program currently is looking at codification for materials in inelastic service. This next slide has a summary of the two topics that are of interest. RC 3.1 looks at advanced high-temperature alloy scoping irradiations. And this topic is to address the need to understand what happens to the material under a radiation environment, particularly in a fast reactor irradiation environment. So these materials are primarily of interest for the sodium fast reactor, but other reactors are looking at these same materials, so research in this area will be applicable to more than just the sodium fast reactor. The second topic is dissimilar transition welds. This material issue has been well identified throughout the years. In fact, the reference in the solicitation that you'll see is from 1983 related to the Clinch River reactor. And the focus for this topic is very narrow in looking at these dissimilar metal weld joints, what's going on at the joint that leads to decrease in mechanical abilities, and how we can improve them. I will mention that the solicitation has a lot more detail on both of these topics. I encourage you to take a look at them. And more information can also be found on our website, nuclear.gov. In particular, there is a report that was completed last year by an independent technical review panel to evaluate what the R&D needs are for this program. So that report has a very good summary of what is of interest in particular to these programs. So now I'll go into a little more detail on both of these topics, starting with the first one, which is the high temperature alloy scoping irradiations. Understanding what the effects of neutron damage are on materials is vital to nuclear reactors, both for operation and for safety and design. Irradiation causes changes in the microstructure. These changes in the microstructure then cause changes to the mechanical behavior and the fracture mechanics of the material, and that needs to be very well understood in order to be incorporated in the design, in order to be for the material to be codified, and also once that understanding is there, advanced materials can be developed to help mitigate the damage and the effects of irradiation. There's two specific alloys that are of interest to this first topic. That's the ferritic martensitic grade 92 and the austenitic alloy 709. These two alloys are of specific interest because of their potential for operation at higher temperatures. These higher temperatures will allow the reactor and the reactor system to be more thermally efficient so that electricity can be produced in a more efficient manner, bringing down costs, and it also helps to increase in the safety margins. However, in order for these materials to be used, their irradiation effects need to be well understood. So this slide has some more specifics. The proposals are sought to develop a mechanistic understanding of irradiation-induced microstructure evolution, and because fast reactors, use of fast reactors is extremely limited, we need to use surrogate irradiation tools. And so understanding how these surrogate irradiation tools correlate to effects in a fast reactor is vital, and that's one of the main focuses of this topic. Modeling and simulation is a very good tool in helping to understand that correlation. These proposals would also include guidance on what future research and neutron irradiations are recommended to support the qualification of these materials. The second topic has to do with transition joints, and this is the dissimilar metal wells issue. As I mentioned, this issue has been identified for quite a while and is very much an issue, particularly at high temperatures. We have some listing of what some of the applications are, and one of the main issues with these dissimilar wells are the reduced creep properties, particular creep rupture and creep fatigue. There's many factors that lead to the premature failure of these types of wells. The differences in coefficients of thermal expansion is a big factor, particularly at these high temperatures that we're talking about here. It adds a lot of very localized stress. Another issue is the proclivity on the ferritic side for oxidation, which leads to oxide notches, which can further increase the localized stress, which leads to strain. Another area and rooms for improvement is in the development of filler materials. There are challenges with both nickel-based and stainless steel filler materials, and research to optimize these filler materials is very attractive. The next slide has some photographic proof of what problems we have in dissimilar metal wells, fracture at fission lines, the oxide notching, creep cavitation. It's all right there. And here we have the specifics of what's looked for, what Bill is looking for in this this particular topic, and mainly to develop testing strategies in order to code qualify alloy 800H wells to 2.5 chrome 1 moly steels for VHTR steam generator applications. And so this research would include understanding what's going on at the wells. Modeling is a very good tool in order to achieve that goal, as well as experimentation. And using that knowledge, also the development of optimized filler metals and any type of novel technique in order to help increase the creep behavior of these wells. And that is all that Bill has prepared for me. But before I move on to questions, I will mention to the researchers that are interested in wells, I'll give a little commercial for my talk at 3:20 on Eastern Time, and my talk will be for the Nuclear Energy Enabling Technologies Reactor Materials area, where our focus will be on joining. It will not be as specific as this joining issue. It will be more cross-cutting joining issues. But I encourage you to come back at 3:20 for that if you're interested in joining.
We have two questions.
Okay.
The first is, what about SCWR supercritical reactors? I don't see it on the list on slide 3.
That reactor isn't currently one of our reactors that we're focused on, and Bill made a very concerted effort to focus the topic this year. And so it was not included.
I am hoping to study near atomic scale properties of high burnup fuel structures, HBS, focusing on near rim region containing recrystallized surrounding rim bubbles. Which group would be possibly interested?
That would probably be in the fuel cycles area, since you are talking about cladding is usually grouped with the fuel. I don't know if that particular area is of interest to them, but I encourage you to look at the section on the fuel cycle.
Are other structural materials, e.g. concrete, of interest in this call?
No, as I said, Bill is very focused on what he's looking for in this call, so concrete is not included this year.
How does RC 3.1 differ from the recently awarded $5 million IRP?
The difference is in the focus. This is looking at particular alloys for a particular application. The IRP was a much broader topic with other goals. Part of it was to understand the correlation between neutron irradiations and ion irradiations, but this is much more specific in understanding what those two alloys go through under irradiation.
In 2013, there were awarded proposals on creep fatigue interactions in 9CR1MOV steel welds and alloy 617. Are these materials still of interest in terms of creep fatigue?
The creep fatigue interest is really focused on the dissimilar metal wells, in particular the alloy 800 and the 2 1/4 chrome 1 moly. As I said, Bill is very really endeavored to focus things this year, and so that is his area of interest right now. Of course, we do have research going on in alloy 617 within the programs, but right now for the solicitation, these are our focus areas.
It was noted that there is a need for proposals related to irradiation of SFR materials. You noted that surrogate irradiations with ions are requested. Will you accept proposals to analyze materials irradiated in reactors if it can be done within the budget?
Yes, as long as the focus of still understanding the correlation between ion and neutron irradiations is still there as part of your proposal. So if part of that understanding comes out of also examining previously irradiated materials, then that would be fine, yes.
Can modeling only work be supported, or does there have to be associated experimental work?
I think it would be very challenging to meet the goals of the solicitation without experimentation included. I think that a very strong case would have to be made by the proposer that we already have the experimental data needed to validate any type of modeling that is done. So that's the challenge with not having experiments included in the proposal.